Hello, I'm Caleb.
Hi, my name is Sophia.
We're Team 138, Projeto from Brazil, University of São Paulo. And today we're going to talk about our research on trading edge airfoils. First, I'm going to give you an overview of what we are going to go through today. We're going to talk about the airfoils and why they're important. And then they're not perfect, so we're also going to talk about the problems and what we try to attack and solve here. Then we're going to look at the motivation and inspiration that we got to solve this problem. And then get into the simulation, how we validated this model we made. And finally, our results.
So let's start talking about airfoils. So airfoils are commonly used in aerodynamic applications due to its property of increasing the lift over drag ratio. So we can have asymmetric or symmetric airfoils, and the symmetric airfoils will only generate lift when it's submitted to an angle of attack in relation to the flow. So for the rocket, for example, airfoils are really useful for the fins because you can enhance fins performance just by changing the profile section that you are using. And comparing a flat fin with an airfoil fin, you can see that the lift generated might be greater than the one you have with the flat fin, and also you might compensate a possible increase in drag with the airfoils by just making smaller fins, because once you have a greater lift, you can have more fins to kind of compensate this setback from using airfoils. And Projeto started using airfoils in 2020, which was when we developed the Europa rocket, which was a rocket developed during the pandemic. And here you can see images from simulations we ran with Rocket Pi, which is the 6 degree of freedom software developed by the team. And here in the red line, you can see a rocket that has fins with airfoil, and the blue line is a rocket with just flat fins. And this is the only difference between those rockets. And as you can see, we were able to reduce the drag generated, the total drag generated, and that led to an increase in the average. And that was good for us. So since then, we've been using airfoils. The airfoil we use is the NACA 12 because it matches our requirements, and also it has a more vast documentation, and you can also develop more projects from that. So, although we have a lot of advantages of using airfoils, there are still setbacks, mainly concerning manufacturing and also the structural strength of the airfoil. When it comes to manufacturing, it's really hard to capture this sharp leading edge that we have at the end of the airfoil. So here, as you can see, we wanted to make a fin with a carbon fiber core and make the airfoil with epoxy resin. But it's not a good fin. It couldn't be used because the airfoil is not perfectly captured. So we had a few limitations on materials and methods. Nowadays we do our airfoil is 3D printed, so we have a more precise geometry, but we lose a bit of the structural strength of it. And this, when we get to this low thickness area, it's more likely to chip and break. And we also must be really aware of how we are handling the fins. And this is not something that is quite practical, because when we are assembling a rocket or even transporting it, like coming to the US, the rocket has to be in an airplane, so we can't guarantee that it will be properly handled all the time. So we couldn't risk having a chipped or damaged fin, because that would generate aerodynamic effects that we wouldn't be able to predict. And also, we want to make our rocket as close as possible to the design and the simulations that we ran. So here you can see this was the 3D printed fin that we used for Genie 2, which was the last rocket launched by the project in the Latin American Space Challenge. And there is a little bit of chipping on those fins. So this was something that we decided that it wasn't good and it had to change for our next rocket.
So once we started to look into solutions for this problem, we noticed that it's not a problem just of ours, but also in several fields of engineering. As you can see on the left, the right figure, there's a car which is shaped somewhat like an airfoil, but it's impractical to make it like full airfoil with a sharp edge at the end. So they have just this cut. And even though they have this cut, you can see the airflow around the shape. It still behaves as if there was an airfoil there. And that's what started to give us some hope that we could just do some kind of like the same effects in our airfoils. In this image on the left, we can see a wind turbine blade, and their problem is more like ours. They want to avoid these sharp edges because it's very prone to breaking and chipping. So they're doing this flat, truncated profile so they can avoid that and also have an easier manufacturing. We also saw that in cycling, as they use thicker and truncated designs of airfoil like this one, it still behaves as a full airfoil while giving them more rigidity in their frame. But we cannot just copy and paste these researches into ours because the boundary conditions is very different from the ones we have in a rocket, right? In a bicycle, we have much lower Reynolds numbers, much lower speeds. Their frames, it's a much more complex design than just a fin. So we cannot use that just like the same thing. And on the other hand, for a wind turbine, we also cannot just copy it because it's going to work in a much higher angle of attack that rockets is not usually subjected to, and it also uses asymmetrical airfoils.
So what we decided to do in order to determine whether we could or not to figure out airfoils was basically run CFD simulations, and we ran with the help of ANSYS Run, we ran 2 CFD simulations to compare the performance of the created airfoils and the standard airfoil. And the first thing we did was to actually validate the model that we had. So we wanted to replicate the conditions that the rocket would experience during the flight. So we found experimental data that was quite similar to the ones that we were aiming. And here you can see the experimental data results for the drag coefficient and lift coefficient on an airfoil. And here we have the results that we got. And we did a model that was AK omega SST2 equations. And we worked with 1.6 million minutes and a compressible flow using the ideal gas and also the steady state density-based simulation. So as you can see, we got pretty good results from this model, and especially for the lift coefficient, we got results that were close enough to the experimental data. The drag coefficient, we expected it to be a little bit different from the experimental data, especially because of our model limitations, because we're working in a steady state and not actually like transient. So we're not fully capable of capturing all this flow separation and maybe recirculation that might surge. So you can see that at higher angles of attack, this is 6 degrees of angle of attack. You might have results that are a bit more different from the original one, but that was a limitation we were aware of. And since we had limited computational resources, we wanted to make it as simple as possible. And also, it's a comparative analysis, so we might refine in the future. So basically, when we say we are truncating our airflow, there are a few strategies to do this truncation. But what we did was basically cut out the last part of it, and it was in relation to the cord. So we basically truncated at 60%, 80%, and 90% of the cord, and we compared that with the standard NACA 12. And we got to, in our final model, we have the 90% cord truncation, and we're going to explain why we decided to go with this airfoil. So basically here we have all the results from drag coefficient and lift coefficient, which were the main criteria for us. And as you can see here on this CL most columns, you have basically the same behavior for lift, which means like even if we are cutting out the last 40% of wound and airfoil, the lift is pretty much the same. And as we also expected, the drag increases as we increase the truncation because we will have more circulation and vortex formation. So this was also kind of expected, but it was good to see that the lift was behaving as the same as the standard version. And here you can see a comparison of the lift coefficient over drag coefficient ratio. And at first sight, it may look like, well, it's not as good as the original and the standard actually airfoil. But since our main goal was actually to not have the sharp plane edge, we decided to take a closer look to how much drag losses we could afford, but also having the same lift, the same stability that we wanted for flight.
So here we have a graph comparing fins with just a flat surface on water, and also having the standard NACA 012 and our 90% truncated NACA 012. And as you can see, both profiles generate a lot more lift compared by angle of attack than just a flat surface, and they're very similar one to the other. In these simulations, we got the 90% truncated, giving a little more lift, but that's just probably just error of the CFG, which is common. So we can just consider this as equal or like mostly equal. And that also shows that it's still much better to use a truncated airfoil than just a flat plane airfoil, flat surface airfoil, because it will give the same benefits. And looking at some results in images and just comparing, so in that side you have the standard NACA 012, and on this side you have the 90% truncated airfoil. And as you can see, the static pressure at 0 degrees of angle of attack, there's almost no difference between the two images, besides that this small area right here, which is slow pressure area. So that goes in line with what we are seeing before. It's just generating a little bit more drag when compared to the standard one. Looking at 6 degrees of angle of attack, we still see the same behavior here. It's a little bit difficult to see, but it's like smaller pressure here. And what we see now is also the difference in pressure that generates lift in the airfoil. And as you can see, most part of the action happens in the front part, front half of an airfoil, which also gives the idea that we could go for more extreme truncations and still have the same lift coefficient being generated, or at least little impact on that. The main problem would still be the drag, which keeps increasing as you cut the section a bit thicker. Here we can see the velocity, again at 0 degrees of angle of attack, and again we see the same profile, the same airflow in both sides, except for this part where we have no air, which goes in line with the static pressure. We said there's a smaller pressure here, so it's slow moving air in this part. Again, endorsing the idea that this is generating a little more drag. And then for 6 degrees of angle of attack, we see the same thing. The behavior is literally the same, except for a smaller, a bigger blue area down here, back here. So that's it. And this is our final design. So it's a very small change, it's very subtle, and we also know that we are losing a little bit of that lift over drag coefficient ratio. But that's a small price to pay, because now we have this profile that we tested, and we see it can like take more hits and not get chipped or broken. That means our simulations is more representative of the real world body, which is very important for us. So now we can actually predict what's happening here. On the other hand, if it chips and have that kind of damage, we cannot know that. So that's what we are gaining here the most. This is some of our references, and we did see a lot more techniques of truncation, some different methods that we want to explore in the future. There's a lot of space to change in there. But we didn't right now because of our resources. And once you have a final design or some final design, we are planning to have some experimental validation in wind tunnel as well. And that's it. I want to give a special thanks to our sponsors and thank you for your attention.
Hi. So you were talking about how there's a trade-off between your drag and your lift. Did you manage to see what that had on your effect on your simulation, and like what that did to your apogee and your trajectory in general?
Yeah. So the increase in drag was very minimal. So when we put that in our trajectory simulation, there was literally no change. So like really minimal in just the fees. So the main rocket still generates a lot more drag than just that.
Yeah. You mentioned you 3D printed the fins. Now, did you end up glassing them with carbon fiber, or just straight 3D printed?
Like we still have the core, the carbon fiber core, but the airfoil is made as 3D printed, so it's put together with like special glue for epoxy and delimiters. So, but it's still with the carbon fiber.
The big advantage of the 3D printing is that we can capture like complex design.
Yeah.
I think you also mentioned something about when you did your CFD, you had experimental data to compare it against. Could you explain a little bit more about that experimental data that you used?
Sure. Yeah. I think it's better. But here the experimental data that we got is from the Aeronautical Research Council. So basically, there are many studies around that pretty much take airfoils and put in wind tunnels and describe their behavior. So we got one of those studies, and there was there were many sets like Mach 0.3, 0.4, and Reynolds number rang from something like, I don't quite remember, but it would go up to like 3 million Reynolds. And we pretty much found the best experimental data that would match the conditions that we were in, that were the rocket conditions that we predicted from our simulations. So this is available. These are publicated studies. You can have access to them.
And this was for the same shape that I had a couple of.
Yeah,
Yes.
same shape.
Cool.
Do you consider any sort of practical consequences to this in terms of, say, mounting or accuracy, asymmetry of the actual flight? I mean, that's your assembling systems. Does it make it any harder, easier or harder?
It makes it easier because before we needed to handle with a lot more care, and any accident may be just like moving the rockets or the fins, or maybe just one pin fall out, and it wouldn't break, but there was these small chippings always occurring. So now we have a much easier way to work, and exactly the same process as before. It's just safer
And
for us.
even like for capturing the geometry, because the 3D printing that we have access, they have a precision. So even for the trailing edge, it was better than using, for example, the epoxy resin. But it was still, sometimes there was still like small defects and things that weren't quite good. So our final fins are way better than the ones we had before.
Yeah.
So if I understand correctly, you have like a carbon fiber core and like a sandwich of 3D printed parts?
Yes.
Just out of curiosity, have you guys considered doing like a non-planar 3D prints? Because I think that would be like the perfect opportunity for that, because then you have the flat planes and you have the airfoil profile on top, right? So if you do a conventional 3D print, you get the layers. But there are, I don't know, I saw some YouTube videos of people like doing non-planar stuff, and they are able to like make the nozzle go up and down, and then you have maybe a better surface, maybe less finished than that, or maybe just Looks good.
You mean like, I don't know if I ever got it.
Because there's a method called like non-planar 3D printing where you don't like do the layers. You kind of do the layers and after that you finish off with the nozzle like moving on the z-axis and the y-axis at the same time.
Would it be something like this? I think. Because we have like here, it's not a planar surface. It already has like a curvature here.
Yeah.
Is what you're asking?
Yeah, just like the method of 3D printing is like the conventional one, or if you guys tried another one that could do like non-planar.
So you're talking about printing it like sideways on the
Yeah.
table? Yeah, so usually we print like this, so it's easier for the print to this. Because if we print this way, then it's harder to keep this geometry. It can like just fall.
Because I thought because of the core, you guys would like sandwich stuff, but you get the core that you put over.
Yeah.
Yeah,
Okay.
that's it.
It's like one piece.
Yeah, easy. For sure.
With your new design, other than the chipping structural value you get from that, have you checked how the structural stability is with that end cutoff? Like, are you, one of the previous photo sessions talked about thin flutter. Have you checked if thin flutter is an issue for you?
Yeah, we did have structural analysis for it, for significant flutter on the fins, and it was safe. Actually, it was better because we wouldn't have the sharp trailing edge, and that would be like the most prone section to have something because of its thickness.
Very fun. Perfect. That's a great job. Thank you guys so much.